record this and then I'll pick the better of the two recordings. Hello to those of you who are joining us on YouTube. I hope that you find the session helpful. And so let's just take a look at the agenda for today. So if you joined us yesterday, it is exactly the same thing. So if you have other stuff to do, I will not be offended in the least if you want to make tracks. But otherwise, yeah, everything that we covered yesterday afternoon, we're going to do again this morning. We just do 2 sessions for those people who can't join the first or the second session. Try and make it easier. Right, so the plan for today is just a basic overview of algebra topics. We're going to go through trig, graphs and theory, and then of course do equation solving. We're going to look very briefly at analytical geometry, and then look at functions and graphs, and integration and area under a curve. Now, Euclidean geometry has a star next to it because, to be honest, I'm not a huge Euclidean geometry fan. So we have asked an expert, Kevin Smith from the Handbook and Study Guide series, to help us out with a workshop, and that is being planned for July. But of course, you are part of the email group now, so you can you will be notified when we have the exact dates for that Euclidean geometry workshop. Cool. So Sharpies is a reward program for maths teachers. So if you want to sign up, you can click on that link, and then it just basically you earn points for doing cool stuff like attending webinars and telling your friends about Sharpies and all of that sort of stuff. And then, of course, when you have enough points, you can exchange them for things like headphones and wireless Bluetooth speakers and laptop bags and so on and so forth. So there's a range of things that you can do. You can also donate to the Future Fund as well, if that's something that makes your heart warm. Awesome. And then, of course, a whole list of resources that we commonly refer back to. So you can download the simulator. For today's one, the simulator's at the end. This is the link to the 535. Then, of course, Geogebra, which we find super helpful. And I will share a little bit about Geogebra when we do the Trigonometry Graphs. Really just nice for class exercises. And then, of course, Maths at Sharp for those worksheets if you need any. Then some other lists of worksheets. These are all actually American worksheets. So you've just got to sift carefully through some of the stuff. But with technical maths, they do tend to do stuff that in America that we don't do in pure maths, but we do in technical maths. So things like radians and so on. So you might find it helpful to go and look, particularly through this mathwarehouse.com worksheets link. And then, of course, if you still need the ATP documents, there's a link to that as well. Now, the calculator we are going to use today is the W506T. It's a pretty epic calculator. I'm not going to lie to you. It's got all sorts of amazing features. And here are some basic features. So, of course, mode to get you to different modes, second function for all your orange functions, alpha for your statistics, and the constant conversions functions. Then, of course, BS is for backspace, and that just deletes whatever you've typed in case you make a mistake. Okay, so not what your kids write when they don't know the answer. And then, of course, change will just change the answer from a third or fraction into a mixed fraction or a decimal answer. And then, of course, you do have the option to include recurring decimals into that set as well. So then you can see the recurring and the recurring notation as well. Okay, and then, of course, equals, which will find the solution. Cool, so these are the different modes we're going to be using. In fact, we're just going to stick to normal and table today, but complex you use, I think, in term 3 as well. And of course, equation solving for algebra, which is really silly for not including today. But the rest of these are not important for today. All right, then the W506, the older model that we had, has been discontinued. It's no longer in stock. So unfortunately, we can't give these to you at that ridiculously low price anymore. Fantastic. So let's jump into algebraic basics. So the first thing that we wanted to show you was the prime factorization. So I'm just going to actually do it on my calculator so you can see. And you can see this from yesterday afternoon's lesson, but we'll get there, don't panic. So all you do is type in the number, and then you press equals, And then we just say second function and exp for prime fact, and that will just break up your number into prime factors. This is particularly helpful when you start solving exponential equations. Okay. Then, of course, from there, I'm actually just going to stay here. From there, we've actually added a highest common factor and a lowest common multiple function to the calculator. So if, for example, you wanted the highest common factor of 36 and 48, for example, then we can say second function and GCD. GCD stands for greatest common divisor. It's exactly the same thing as highest common factor. And then let's say 48 and equals. So we know our highest common factor of 36 and 48 is 12. This is particularly helpful when they start doing factorizing of trinomials and so on. And then, of course, you can just add as many numbers as you like to the string. I've tested it and had 64 different numbers. Obviously, it depends on how many characters you insert, but basically, it doesn't matter. I mean, you can put 5 or 10 if that's something that you wanted to do in here, and it will find the highest common factor for you as well. And then, of course, your lowest common multiple. So let's say we have 36 and 48 again. This time, we just say second function and 3, and then 48 and equals, and that gives us 144. And if we included 72 in it, like so, still 144. So it's good to know that that is all multiples of 12. And my maths has not gone completely crazy. Thank you, Haley. I like it too. Awesome. Okay, so let's head back here. So here are all the steps. I will send you this PowerPoint presentation as a PDF on Monday, along with the link to the webinar that will be uploaded to our YouTube channel. Okay, so if you are looking for resources, then you'll have this PDF PowerPoint presentation for all of the links that are included in it. Now, the next thing that I want to show you is how to find fact pairs of any number. And this is particularly helpful for those students who really struggle with trinomials. So I'm going to build the base with the fact pairs, and then I'm going to actually show you how to factorize trinomials using this functionality on your calculator. So we're going to type in 36, press the fraction button, and then we're just going to press the RCL button twice, and that's going to give us an X. Okay, so we've got 36 divided by X. Essentially, it's just a very big hyperbola. And then we say equals, oh, sorry. You know what I've done? I haven't gone to table. Okay, so go to table mode first. Then 36 fraction, and then RCL. And then your equals button. We're going to leave function 2 as it is for now. So we're just going to leave it blank and then press equals. We'll leave our start and step at 0 and 1. Very basic and simple. And here are all of your fact pairs: 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 and 7.2. So we can safely ignore 5. 5 is not a factor of 36. And then, of course, 6 and 6. And here we can see we've got 7 and 5. So we've looped through and we know that we've got all our fact pairs of 36 very quickly. Now, let me just go back up here because I didn't mention this just now, but this is your asymptote. So when you have a stripy line, and we'll come back to that later, it's where your graph is undefined. It doesn't exist at this point. So you have that little stripy line as well. All right. So from here, what I want to do is I want to do a very basic example of factorizing with you. And just go through the basic rules. So what I always tell the students is to first look at the sign at the back, the sign in front of your constant value. Okay, so if the sign at the back is a plus, it means that my signs in my brackets are going to be exactly the same. And I know which sign to use by looking at the sign in front of my coefficient of x, or my b. So here, when I write down my brackets, I can just write x plus and x plus. And it tells me, the back plus sign, that I must add my two factors together. Now here, I've got a sign at the back that says plus, but my sign here is a minus. So what I'm going to do is I'm just going to have two brackets with minus signs because my signs are the same. When I have a sign that is a minus at the back, it means that my brackets are going to have different signs. And I'll come back to filling those signs in just now when I do the example with you. Okay, so that's so far. Now we need to find all the factor pairs of 6. And we can do this very quickly on the calculator. I'm going to go back here and just do it with you. So we're just going to say I'm actually just going to delete the 3. Okay, so we've got 6, So we've got 6 over x and equals, and again, just skip through all of the other stuff. And here you can see your factor space. So we've got 1 and 6, 2 and 3, 3 and 2, and 6 and 1, right? I'm going to write all of them down just for my example. So here, I don't know why my pen is not showing up. Okay, so we've got 1 and 6, 2 and 3, 3 and 2, and 6 and 1. Now, when the sign at the back is a plus, I add both my columns together. Okay, so they'll either be both pluses or both minuses, but they add together to give this middle term here. So 1 plus 6 gives me 7. That's not what I'm looking for, so I can ignore them. 2 plus 3 gives me 5, so that is what I'm looking for. So here I'm going to have x plus 2 and x plus 3, like so. Now again, we've got the brackets. They disappear when you change functions. So I'm just going to put this back here. Just pardon my handwriting. I'm not very good at mouse writing. So now we've got 2 with 2 factors that add up to 5. So again, 1 plus 6 is 7, not my middle term. 2 plus 3 is 5, so that is my middle term. So I just write 2 and 3 down. Okay, let me just rewrite these here. 2, 3, 3 and 2, and 6 and 1. Now your signs here tell us that they are different signs. So in my brackets, I'm going to have 2 different signs. I'm just going to write my x's down. I'll fill in the signs with my numbers this time. So here I'm going to make this column a plus column and this column a minus column. So plus 1 minus 6 gives me minus 5, not my middle term. So I look at my next one. Plus 2 minus 3 gives me minus 1. So that is what I'm looking for. So here I'm going to fill in plus 2 minus 3, and there I am done. So that's just a really nice way to do factorizing on the calculator, and just basic steps for your students. I'm going to clear this away. It will be on the, on the YouTube video when we upload it as well. Okay, so the next section I'm going to look at is trigonometry. Are we all okay so far? Any questions? We're all good. If you are good and still awake, don't you just wave your hand at me? Awesome, thanks, Haley. Thanks, Mary. Okay, so there are still people out there listening. Okay, great. Thanks, Anna. Fantastic. Polisi, I think I'm butchering your name, but thanks for waving. That's great. Okay, so trigonometry graphs. What we did is I just wanted to show you how to investigate these trig graphs just with your table mode and just drawing them for your students to see. So I'm going to do the very first example with you. And then the next ones I'll sort of breeze over because it can get quite a bit repetitive. So I just want to, I don't want to bore you all to tears, but it is something that's really nice for exploring different graphs and the effects of A, P, and Q on the graphs. Okay, so we're just going to start off with the basic sine graph. So I'm just going to make an X, so RCL twice to make an X. And I'm going to press equals. And I think for now, we're just going to leave function 2 blank. And then let's start at negative 180. Now, when you're filling in this here, remember not to use your minus and to rather use your negative sign, because minus is a function, negative is a value. And otherwise, it will give you an error when you use minus. Okay. And then instead of making our steps 1, which we could do if we really wanted to, we're going to make our steps 15, just so that we can sort of see a nice curve and not get shark teeth. So here are all of our steps, or all of our coordinate pairs. And you can see some are nice to plot, others are not so nice to plot. But it does give you a fair idea of sort of where the points belong on the graph. Now, what I did is before this, I went to Geogebra. And then I realized my Geogebra was really old, so I went and downloaded the new version, which is awesome. And while I was looking through Geogebra, I found this, which is a Geogebra classroom. And I thought it's such a great thing for maths teachers to be able to use. So what they've actually done is they've created a way for you to create a class activity, and then for all of your students to join that class activity and then to do different activities. So you'll see that this picture actually is linked to GeoGebra, this link here. So if you just click on the picture when you get this PDF version of PowerPoint, you will be able to go directly to GeoGebra and set up this classroom thing if that's something that you wanted to do. Then this has, so GeoGebra has set up 2,200 different resources that you can play on GeoGebra or do on GeoGebra, different interactive resources. So, I mean, you really have a lot of cool stuff here. You know, probability, trigonometry, functions, calculus, lots of awesome stuff that your students can play with and that you can share in class with them. So again, this picture is also linked. You can just click on the picture and it will take you directly through to the website. Okay, so then I tried to plot a sine graph on GeoGebra, and let me just tell you, it was quite a thing. So I just wanted to give you some tips and heads up. If you want to directly plot a sine graph onto the GeoGebra functionality, it's not as easy with trigonometry. It's much easier when you're doing straight line graphs and circles and all of that sort of stuff. And so functions and Euclidean geometry are wonderful. So, trigonometry is a little bit more difficult. So here you can see that we've gone through and created this graph and then shifted, or I think I created a cos graph here. The red one is cos and the green one is a sine graph. But in order to get this graph to look like this, you actually need to change the units of the graph. Because otherwise GeoGebra is going to plot it in radians. So these are the different steps that you can follow to make sure that you get this sort of graph on your own side. Okay, so what I did is I took the coordinates pairs from the table and I plotted them on GeoGebra, and here's my sine graph here. And then just another thing to note is when you're plotting those coordinates, if you don't know this already, don't use a semicolon. This thing over here, you need to use a comma because a semicolon changes the units of the coordinate pairs. I don't know what it changes them to, but it will completely destroy your graph. So just a heads up on that one as well. And then all you would need to do is take your pen and connect the dots. Okay, now please give my penmanship here. I have been practicing. So there you go. So that is a sine graph. And then we can go further and start investigating the different effects of A. Okay, so what we're going to do is on the calculator, I'm just going to go back here. I'm going to leave the sine graph as it is. And then here, I'm going to make it 2 sine, oopsie, sorry, sine x. Okay, and equals, again, because they'll stay the same because you haven't changed modes. And now you can see the effect of your A. So here we can see that it's literally doubled the value. And if I go down some more, let's go look for some more nice values. Here you go. -1 times 2 is -2. And I'll keep going. -1/2 is -1, and so on and so forth. So what we did is we went and plotted this graph, which again, you can do with your students. So my blue one is my original graph, which is this one here. So it just floats between -1 and 1. And then your new graph with the A equal to 2 floats between 2 and, sorry about this, poor penmanship, and 2 and -2. So you can see the graph has just been stretched out. These points here have stayed exactly the same, right? But the middle points where the graph, your wave part, has actually just become bigger by 2. Okay. So from, yes, I see a question. Thanks, Anna. Awesome. So here we're going to go through and then we're going to look at what the effects of half and if A is half. So I'm not going to redo it on the calculator because you sort of get the idea. But you can see from the graph points that I've plotted again. So here's my blue graph here. And here's my new graph. So I try to keep it in theme. So red is the new one and blue is the standard one. So there you can see that now your graph is half the size of the other graph. So we can see that the effect of A determines the size of your wave, how big or how short your wave is going to be. And of course, you can go and do lots of other things with this. You can investigate the shift up and down. I'm not going to go through all of these steps with you, but you can follow along with it in the PDF. So here, if we draw the graph, oh, let me just use red because it's already red, and I'll come back and do blue. Here's my red graph, and my blue is here. There we go. Now you can see that all of the points are exactly 1 unit apart from each other. So you can see when your shift is, when it's Q and it shifts the graph, it literally just pushes the graph upwards by however many units, or if it's a minus Q, shifts the graph downwards by however many units. So again, just a really nice way to explore what's going on with the sine graph. And then, of course, again, if you are shifting left and right, and I think a lot of students struggle with this particular section because the shift is not intuitive. Because your original equation is x minus p, when it becomes x plus p, you're actually shifting towards the left, right? This way, when it's minus p, and when it's plus, so it's x plus whatever in the brackets. And then when it's x minus, it's shifting this way. But that doesn't make sense when you think about your Cartesian plane. And that's because we have to remember the original equation is actually x minus p. So it's x minus p is equal to 0. So it's x is equal to p. And that's why your shift is to the right. Whereas here it will be x is equal to minus p. And that's why your shift is to the left. Okay. Cool. So again, we just drew the graphs quickly. I'll just do it for you quickly here. And you can see from my graph that everything else is exactly the same. The shape is the same. It hasn't moved up or down. It's just shifted 30 degrees. Every single coordinate here, you can see it's shifted 30 degrees. Okay. So it's just a really nice way, again, to explore this whole concept with your students. And because you have a lot more time in class, you can spend a lot more time doing these coordinate plots and so on and so forth as well. All right, cool. So from there, I know we just use sine as the examples, but again, you can plot your cos or your tan as well and do all of those different shifts with them to make it slightly more interesting. I just use sine because I had those original coordinates there for me. Now, from here, we need to know trigonometry graphs in order to be able to solve trig equations, because a lot of what comes from your trig graphs feeds into your equations of it. So just some points to note: always start the furthest away from your x, and then remember that your trigonometry ratio on the outside. So if x is in brackets or there's something multiplied to the x, then that is inside the trig ratio, and you need to deal with the outside, which is the trig ratio first, before you deal with that 2x or that x plus 30 or whatever else. Okay, and then remember how often your graphs repeat, and that will help you with your general and specific solutions as well. So here your graphs repeat every 360 degrees, right? And cos will be like so. And tan is every 180. Okay, so it's just something that you need to be aware of as well. So I've done 3 different examples here. I'm going to go through the first 2 quite finely, and then tan I'll just do a little bit quicker. Okay, so here we've got 3 sine is of x plus 30 is equal to 1. So here you can see in brackets, this is x plus 30. So this is the last thing that we're going to deal with. So we deal with the 3 first, we take it to the other side, and now we've got sine x plus 30, is equal to 1/3. And now we need to find the reference angle for this. So our reference angle when we calculate it is sine of 1/3 is equal to 19.47. Okay, so we now have a reference angle of x plus 30 is equal to 19.47. Okay, so sine means we need to add 360 degrees, and we have 2 general solutions. The first one is our reference angle, And then we take the 30 to the other side and we just add K360 to the side. The second solution, you need to take 180 and subtract the reference angle from it. And then, of course, move our 30 degrees to the other side, plus K360 again. So we have these two different solutions here. Okay. Because when we think about a sine graph, it's okay. So it's doing this wave thing, right? Sorry about that. But when you draw it like this, do you see there's 1, 2, 3, 4 points in one every 360. So you actually need to look, sorry, every 2 points in every 360. So there actually needs to be 2 solutions for that. Okay, so from here, what I did is I actually used the table mode to find my specific solutions. And I've never thought of doing it before like this, but it actually makes it so easy. So I'm going to show you what I did. So what I did is I took the specific solution. So it was 10.53 plus, and then instead of K, I'm just going to use X because that's the only thing the calculator knows, and times it by 360. Then my second solution, just to clear any functions, you just press the on button. Okay, so then I have 130.53 times X, oh, sorry, being very silly, plus X times 360. Okay. And if I just press my equals button, obviously now I don't want to start at substituting in K is negative 180. It's going to give me a crazy result. So I'm just going to change it to negative 1. And my step, I'm obviously going to change to 1 because now we're counting in in integers. Okay. So there we go. So we're looking for solutions between 30 degrees and 200 degrees. Okay, so these are both too small. So I look at my 0, that's too small. There we go. So 130.53. And then if I look at my next group, it's 349. So I'm already out of the section that I'm looking for answers for. So actually, my only specific solution is 130.53 degrees. It's quite clever, hey? It's a nice way to do it. So let's do another example just to firm up what we've just dealt with. Sorry. Oh, I've gone the wrong way. Okay. so we have 5 cos of 4x minus 2. So we take 2 to the other side. And then, of course, we divide it by 5. So we've got cos 4x is equal to 2/5. Okay. Now we're going to get rid of the trig ratio because 4x is inside of that trig ratio. So we deal with the cos first. So now we've solved and we can see that 4x is 66.42 degrees. So our reference angle is 4x is equal to 66.42 degrees, and we're looking for specific solutions between negative 180 and 300. So our general solution for the cos diagram is you're going to have 360 minus your reference angle and 360 plus your reference angle to get your 2 solutions. Okay. So, and then of course we need to now divide by 4 for both of those. So our actual general solution are these ones here. Okay, and if you think about it, 4x is the inner part of your cos diagram. So it bunches your waves together. And so you get lots of little waves. And that's why we have so many possible solutions, because your graph is fits into 90-degree periods instead of into a 360-degree period. Okay. So here's our specific solution. Again, I did it on the table, and you'll see with this one, I'm actually just going to go do it on the table because there were so many solutions for this one. So it's 73.395 plus x times 360. And the next one is 106.605 plus x times 90. Okay, so there's our 2 specific solutions, or our general solutions, and then we can go and look for between negative 180. So our first one is negative 286, so we can ignore that. Then we've got 16, then we've got 73, 106, 403 we're going to ignore, 196 is fine. Why is this jumping so quickly? I've done something wrong, haven't I? Oh, there we go. It must be 90. There we go. Okay, so let's go back. So we're looking for between negative 180. Thanks, Haley. I like it too. Yeah, I just discovered it. And, you know, it just makes so much sense, especially for those kids who really struggle with substitution. And you can see what I've done here. Can you imagine if they did that 20 times on the calculator? Then all of their specific solutions are wrong because they've made one mistake. But they do need to go and check and make sure that they can see if something is a mistake as well. All right, awesome. So again, we can do exactly the same thing for tan. The only difference with tan is that there's only one general solution for every 180 degrees, and you can go and look for it in your table over there. So you can see here, there's only one specific solution between 0 and 270 for this question. Now, these questions that I took come out of a maths worksheet. So if you would like that worksheet, just let me know, and I will include it in a list of worksheets for you. So a brief, quick look into analytical geometry. Is everyone happy? We're all still good? Awesome. Thanks, Anna. All right, fantastic. Okay, so some things for analytical geometry that are important to remember. Your straight line formula, your gradients, and the various things that fall under gradients. So for example, the fact that gradient is equal to tan theta, which will give us our angle of inclination of that line. And then of course, your typical gradient formula. And then when your gradient is equal to a second gradient, you know that your lines are parallel. So this works also in reverse. If my lines are parallel, I know that my gradients are equal. So it's works both ways. And then of course your perpendicular lines. So if my first gradient times my second gradient gives me -1, my lines are perpendicular. And we can also use this to prove that something is perpendicular. So we can say, okay, if gradient 1 times gradient 2 is -1, then my lines are perpendicular. And if I have lines that are perpendicular and I have one gradient, I can find my other gradient using this formula. Okay, and then of course a tangent is perpendicular to the radius, so that's where this important information also comes in to play as well. Then of course, if you wanted to find the angle of inclination, it's just something we've done already, but I just wanted to put the steps in there so that you could follow along quite easily as well. All right, so functions and graphs. So we looked at obviously your straight line graph, which you do in grade 8 and grade 9, and then of course your parabola, your hyperbola, and your exponential graph. Now these are the metric final formulas, so don't panic just yet if you're grade 10 or 11. Then some important terms, domain and range. So domain is all your possible x values and range is all your possible y values. So I always remember it in alphabetical order. Domain is before range, D before R, so and X is before Y. So domain and X, D and X belong together, and range and Y belong together. And then of course your intercepts are the points where either your X is 0 or your Y is 0. And that's where the graph intersects with your axes. And then of course your asymptotes, those beautiful electric fencing lines that we have when your graph tries to divide by 0. So it's when it attempts to divide by 0 that you get these asymptotes. And you saw already on the calculator that asymptote before. Then of course your axis of symmetry is the line that cuts through the graph and creates a mirror image. Now some graphs have 2, like the hyperbola, others just have 1, some have none, just depending on what kind of graph you have. And then of course your turning points is only for graphs where your gradient actually changes signs. So when your gradient goes from positive to negative or negative to positive. And the only one really that applies to is your parabola. So what we did is we investigated the effects of your A, P, and Q on the parabola. I'm not going to go through it again because it's very similar in theory to your trigonometry graphs that we've investigated. So I'm not going to do the steps on the calculator. I am just going to show you the effects. So here what we did is we had x squared, and then we multiplied x squared by 2 for the second function. And then if you go and look at my graph here, I'll draw it. Here is my original x squared graph. And here is my new graph that was multiplied by 2. So it's the same graph, it's just multiplied by 2. Now anything multiplied 0 times 2 is still 0. So that's why. And then, of course, you can see your gaps are just growing every time, because obviously a smaller number multiplied by 2 will still be smaller, but a bigger number multiplied by 2, this one was actually off the screen, which is why you can't compare the two of these. So you can see that as when a is bigger than 1, it gets thinner and it tends towards the x-axis. Now we can also go and investigate when my a is a half, which is what we did in this next section, and then we looked at the effect on the graph. So let me just draw this one because it's red already. So here my graph is wider, and then my original graph, which is this one here. So there's a lovely lady at Master Maths in Maysdale called Melanie, and she explains this to the students like this. So the more time you spend at gym, in other words, a is greater than 1, the thinner you are going to become. And the less time you spend at gym, the fatter you're going to get. Okay, now obviously when a is less than 0, which is something we didn't look at here, we're going to get a sad face. So that's also something else that you could investigate with your students and look at the effects of that and whether or not the graph is mirrored and so on and so forth as well. Again, let's look, we can do the shift up and down. And here you can see exactly the same distance between the 2 points every time. So I don't know if you want me to draw this again for you, just to sort of have the image. It's much easier when you're doing it in a book with pencil. There you go. And then here's your new one. Sorry, it's not a very good example. If I drew it on Geogebra, you could see. So here you can see that the distance every time is 2. So the whole entire graph is just shifted up by 2. So when we add something, when we add a q, we know that we are shifting the graph up or down, depending on whether or not the q is positive or negative. And then, of course, again, shifting to your left or right. And here you can see with this shift, that this has actually changed your turning point. Oh, that was a terrible one, guys. I'm so sorry. You can see the turning point here is at -3, whereas the original graph's turning point is here at 0 and 0. So there's two things to pay attention to. The first is the shift to the left for x plus 3. And the second is the fact that your turning point is now shifted from the origin to the -3 as well. Cool. So here is the Parabola Summary. I've just put it all nicely down. You are welcome to use these notes with your students. It just makes a nice way to find everything. Then for the turning points, oh, I did not fix that. I'm so sorry. For the turning points, I thought I had fixed everything. It must be negative b over 2a. And if you're in grade 11, you can complete the square, or in grade 12, you can use the derivative to find your turning points. So your turning point is obviously where your gradient becomes 0. It's where it changes between the two graphs. Then for the hyperbola, you have grade 10 and 11 only use ax plus q. And of course, in grade 12, you include that shift to the left and the right as well. I'm not going to go through all of this again, but you can just see this is the shift up and down. What I do want to show you for hyperbolas, I'm going to go back here to this example. So let's say we have a hyperbola and it's just 2 over x, right? I'm not going to add the second one. I just want to show you this. So we can see here when we draw the graph here. So it goes all the way, all our points reach here. All our points reach here, right? And then we have nothing between -1 and 0. And then the next thing it's at 2 and 1. So it feels like the graph should do this, right? But it shouldn't, because we have a hyperbola. And of course, an asymptote, which we can see when we look at it on the calculator. If I look, there it is, my asymptote. So I know that it doesn't actually connect at all. Now, what you can do is you can go back, and once you've got those original points, you can just change your step to say 0.1 or 0.2, depending on how much effort you want to put in. And you can just go through and look. So we can see at negative 0.8, it's 2.5, negative 2.5. And then at negative 0.5, it's negative 4, which is the point that I've plotted. And then we can see negative 0.4 is negative 5. And you can see it's growing quite quickly the closer you get to 0, which is what you'll see with this tape, the tail here, right? So you'll see, let me just do this. There you go. So you can see that here, you can see this nice tail coming down as you go. And so that's something important to share with your students, that just because you can't see all of the points, change your step. Look at what's happening when your step is really tiny between that point there as well. And of course, it's going to do exactly the same thing here. So here it's progressively getting smaller and smaller, and then it's going to tend towards infinity the closer you get to the 0 asymptote as well. Awesome. Then, of course, your hyperbola summary and your domain and range and intercepts as well. And then, of course, remember your axes of symmetry for this one, there are 2. So you can actually use this formula to simplify finding your C value and looking for your gradients and so on and so forth. Remember your gradients are always +1 and -1. So, okay, fantastic. Then, of course, again, your exponential graph. And you can see it's quite simplified down from the pure maths as well. And I'm not going to repeat myself over and over, but you can see it's just a lot of nice examples to see what you can do investigating the graph. So the important thing to remember here is A determines in which quadrants you are putting your graph in, and the size of your graph. So if A is positive, it's obviously going to be in the first 2 quadrants, and if A is negative, it's going to be in the bottom half. And then remember that B can never, ever, ever be negative, because if it was negative, what will happen is you'll have this skipping. So because when your exponent is even, it will be positive. When your exponent is odd, it'll be negative. So you'd have this like that. So we don't draw graphs like that for exponential graphs. So your B must always be positive. And then when your B is a fraction, it moves from big to small, because the bigger your exponent of a fraction, the smaller your exponent is going to be. And then, of course, when B is greater than 1, the bigger the exponent, the bigger the answer is. So that's the 2 options over there as well. All right, and then of course your domain is all your possible x and y x values. You don't have any restrictions on that, whereas your range will depend on the shift of your exponential graph up and down. So if there is no q, it will just be 0. And then of course, when you're solving for your x-intercept, so you've made y 0, you need to use your prime factorization function, which we discussed at the beginning, in order to find your exponent solution as well. Okay. So circles is covered in grade 12, I think. So just some nice things. So what I did is I also drew a circle on the calculator. I just want to show you this because it's actually really cool. So before I share this, if we just look here, our equation of the circle is 9 is equal to y squared plus x squared. Okay. Now, when we do anything in table mode, we need to get the y by itself. And that's the same for all calculators, not just the sharp. So you need to simplify to get y by itself. So we take the x to the other side, and then we take the square root. Now, when we take a square root of a number, we know that we need to have a plus and a minus. And on the calculator, you cannot add that plus minus function in. Okay. So when we plot the graph, we're actually just going to plot half a graph. So we're going to have the square root of 9 minus x squared, right? And equals, I'm going to ignore function 2 for now. Let's make my step 1 again. And there we go. So if I look, okay, so at -4, my graph does not exist. It's undefined. At -3, it's 0. And then I can plot these points here. And you'll see if we come back down again at 4, it doesn't exist again. And we know that because of the circle. The circle only covers a certain area and then it disappears. Doesn't exist beyond that. So I plotted the coordinates and you can see I've just literally got half a circle here. Sorry about that. That was a terrible circle. And then, of course, if we want the bottom half of the circle, so your students can just use this and multiply them all by negatives. Or what we could do is in our second function is just to make the same equation, but with a negative sign in front. So we're going to do that now. And equals, equals, equals. And here you can see at -3, at -4, it doesn't exist on either side. And then you've got mirror images where one is a negative, one is a positive, and exactly the same for all of them. So now when we go and we plot the graph, you can see there's my circle, and you can actually see the shape of the circle. Now I'm not going to attempt to draw this. I drew it in Geogebra so that it was nice and neat. So there's my beautiful circle. And you can see it's really nice and easy to put the coordinates and work through the exercise of drawing a circle. And of course, the smaller you make the steps, the closer you can get these points on the circle. But that's really up to you and the exercise that you do with it. Cool. Are we all happy with that? With graphs? Thanks, Haley. Fantastic. Thanks, Nelly. Scalisi. Thank you so much. I'm sure I'm supposed to click when I say your name. I'm sorry. My tongue does not do that. Okay, so the next thing that we're going to look at is differentiation. Now, for technical maths, you can actually use this calculator, but in pure maths, you can't. So just a heads up on that difference, because the pure maths does not allow the equation solver in the final exam. So just if you are a pure maths and maths teacher, just a heads up for that. Thanks, Timberlake. I'm glad to hear that. Oh, Lichle, right? Okay, awesome. So let's just do a differential. So we're going to use our alpha button, and you can see the ddx is on your closed bracket. And so what you do is you put the algebraic expression at the top, and in the x, you put your point. Now, the calculator is not going to give you an algebraic expression back. It is only going to do a decimal or an integer answer for you. Okay, so you cannot use it to see whether or not you've differentiated correctly algebraically. But if you do substitute into your solution that you found and then use the same value here, you can check that they are both the same, and that should help you make sure that you've differentiated correctly. And then, of course, we're going to make it 3 over here and equals, and it gives us 93.0000. So the calculator doesn't solve things algebraically. It uses a Newtonian method of approximation, and it just gets the answer closer and closer and closer and closer to what it's supposed to be. So that's why you get this, because it's got a margin of error. So we know that the answer is actually 93. And I mean, there's enough zeros there to make it insignificant for you, but just so that you know what to look out for when you are doing these. And then, of course, integration. Let's do integration as well. So the integral is on the open brackets button, and that's just to find the area under a curve. Again, it's not going to give you the algebraic solution. It is just going to give you a number or decimal answer. Okay, so if I'm looking for the area under a curve between 1 and 3, and my curve is 3x cubed minus 5. I see a question's popped up. I'm going to deal with it in a sec. And equals, and there we go. So the area under my curve is 50 units. Oh, yes, Anna, but don't worry. We'll send you a W506, so you'll have a new one, which is exciting. Cool, awesome. So that is the end of this section. To those of you who are watching on YouTube, thank you so much for joining us. We hope you found it useful. Please subscribe.